I would like to thank the organizers for inviting me to this conference. I'd like to talk about classification of Saturn.
No, that's not.
What do you?
Is this microphone?
Yes.
No, it's not. 이거 저거죠? 그 사람들이 오해를 하는데. Could you move this one?
Okay. I'd like to talk about classification of Saturn complex manifold, which is equipped with torus action. First, I'd like to introduce maximal torus action. So for a moment, we consider smooth case. So let them be a connected smooth manifold equipped with effective torus action. So for point x in M, the tangent space is a faithful representation of the isotropy subgroup G sub x. And the tangent space G sub xm is decomposed into the following subspaces. So one is a subspace tangent to the orbit. So this is a trivial representation of G sub x because G is abelian. And the other one is it's normal. So this is faithful because the whole space Txm is faithful. So the associated homomorphism. Associated homomorphism. So this is a homomorphism from G sub x to the general linear group of this one, and this is injective. So we have a following inequality. So the dimension of the isotropy subgroup should be less than or equal to the half of the dimension of this vector space. Otherwise, we cannot embed G sub x to this D group. So we have this inequality, and this inequality can be simplified to the following. So the dimension of the torus and plus the dimension of the isotropy subgroup is less than or equal to the dimension of the manifold. So we focus on this inequality and consider the extreme case. So let me show you an example. So if there is a fixed point, the dimension of G should be less than or equal to the half of the dimension of whole manifold. So this is a well-known inequality. Okay. So now let me define the notion of maximal torus action. So let M be a connected smooth manifold equipped with an effective torus action. We say that this action is maximal if there exists a point such that the equality holds. Okay. And so let me explain why I call it maximal. So this is here is a proposition. So let G prime be a compact torus acting on a connected smooth manifold M effectively. And let G be a subtorus of G prime acting on M maximal in this sense. Then G coincides with the G prime. So I mean, so there is no large action of a torus on M. So proof is very easy. So because G prime acts on M effectively, we have a following inequality for any point. And by definition of maximal torus action, Z exists at point X such that the equality holds. And we choose X such a point, and we have then since G is a subtorus of G prime, we have an inequality, and at this point we have also an inequality. So dimension G prime should be equal to the dimension of G. So we have G coincides with G prime. Okay. So this is the purpose of this talk. So we consider the following. So M is a connected compact complex manifold. And we consider maximal torus action on M, which preserves the complex structure on M. And the purposes of this talk are following. So one is to describe such a pair, so namely complex manifold with maximal torus action with combinatorial data, like toric geometry. And I also like to talk about non-equivariant version. So I mean classification of such a manifold up to bihomorphisms, not equivalent bihomorphism. Okay. Let me show you several examples. So this is the simplest one. So we consider the quotient Cn over gamma. Here, gamma is a lattice of Cn. Then, and let G be the same as M. And this is 2-dimensional torus as real Lie groups. Then for any point X, the dimension of G is 2n, and the isotropy subgroup is trivial, so the dimension of G sub X is 0, and the sum of these guys is equal to the whole dimension. So this is the maximal torus action. Okay. Next example is complete non-singular toric varieties. So let M be a complete non-singular toric variety of complex dimension n. By definition, there is an n-dimensional algebraic torus action on M, and let G be the compact factor of C star n. Since M is complete, there is a fixed point. At the fixed point, the dimension of G plus the dimension of G sub X is equal to the dimension of M, because dimension G sub X is the whole G. So in some sense, the converse is also true. So namely, Hiroaki and I have shown the following. So let M be a connected compact complex manifold of complex dimension n. So suppose S1 n-dimensional torus acts on M effectively and preserves the complex structure. We also suppose that there exists a fixed point. So in this situation, this is maximal, because, as I said, the isotropy subgroup is whole G. So in this situation, we can say that the manifold M is actually equivalently bihomorphic to a toric variety. So we can classify such a manifold. Okay. The next example is Calabi-Ekman manifold. So we consider system action on the product ck minus 0 times cm minus k minus 0. The action is defined by the coordinate-wise multiplication. Now we take a complex number, not a real number, and consider the subgroup of system defined by like this. And the quotient space is one can see that the quotient space is a complex manifold which is diffeomorphic to a product of odd-dimensional sphere. And so this is a closed complex manifold. And we consider m-dimensional torus action given by the same formulation. Then for the point x, the first entry and k plus first entry of x is 1, others are 0. So this is a point in M. For the point x, the dimension of G plus dimension of the isotropy subgroup is the dimension of the whole manifold. So this is a complex manifold with maximal torus action. And I should mention the earlier works, which is a motivation of this talk. So moment angle manifold with complex analytic structures and LVMB manifolds are generalization of Calabi-Ekman manifold. So let me explain their construction briefly. So let U be a complement of a coordinate subspace arrangement of Z in CM or CPM. And we consider subgroup H, which is isomorphic to CL, and system acts on U, so H also acts on U. So for some special U and H, the quotient space becomes a closed complex manifold. So there's several people study such an object. And it's not difficult to see that the compact torus action on the quotient space is maximal. So moment angle manifold and LVMB manifolds are also examples of complex manifold with maximal torus actions. So what I wanted to say is, so there are many examples. Okay. Okay, let's return to our general situation. So let's recall our setting. So M is a connected compact complex manifold, and G is a compact torus acting on M maximal and preserving the complex structure. So we will assign two invariants to Mg. So one is a collection of cones in G. G is a real algebra of G, as well as toric geometry. The other one is a vector subspace of G. G is a complexified vector space of G. Okay. So first, I would like to explain how to assign the fun from to Mg. So let's consider one-dimensional subtorus G prime of G. Of course, G prime is a compact Lie group, so each connected component of the fixed points set is a complex submanifold of M. So now we define a notion of characteristic submanifold. So characteristic manifold is a complex codimension 1 submanifold, which is a connected component of the fixed point set by a one-dimensional subtorus G prime of G. So this is an analog of prime toric divisor. So using characteristic submanifold, we can define fan. And since M and G both are compact, so we can say that the number of characteristic submanifolds is at most finite. Okay, so let M1 MK be characteristic submanifolds and let GI be the one-dimensional subtorus which fixes My pointwise. We consider parameterization of GI, and there are many parameterizations, but we can choose a special one using this way. So the normal bundle of characteristic submanifold is a line bundle over Mi by definition. So so we choose the parameterization lambda I, so that the weight on normal bundle is exactly 1. But anyway, there is a special homomorphism from S1 to GI. And we think of this homomorphism as a vector in Gay as follows. So the homomorphism, the differential homomorphism is a linear map from R to Gay, and the image of 1 is an element in Gay. So we can think of lambda as an element in Gay. And now we define a collection of cones in Gay, so that for the set of indexes, if the intersection of characteristic submanifolds corresponds to I, the capital I, is not empty, then we add the cone spanned by lambda i's to the member of delta. So then we have a collection of cones. Okay. And now we define another invariant. So by compactness of M and the action preserves the complex structure on M, so we can define complexified action. So this is GC is an algebraic torus, and the action is holomorphic action. Then we consider the global stabilizers. So namely, this is a subgroup, and each element fixes all points in M. So this is a complex analytic subgroup of GC, and its real algebra is a complex subspace of Gay. So here, X sub U denotes the fundamental vector field generated by U, and the real algebra can be the real algebra of H can be represented as like this. Okay. So we have assigned two invariants. One is a collection cone delta, and the other one is a complex subspace of Geshi. And so these invariants are controlled as the following proposition. So this is a little bit hard to understand quickly, but let me explain. So the triple delta has G. So G is a box of the found complex subspace. And the triple satisfies the following. One is the collection of cone is actually a non-singular form. So here non-singular means with respect to the lattice. So the lattice is the set of homomorphisms. And next, second, for the projection Geshi to Gei, its restriction to her is injective. And third, for the quotient map from Ge to the image of for the Ge to Ge over P her, the quotient map sends this fan to a complete fan in a vector space. This vector space. So I'm not going to explain the proof of this proposition, but let me explain why we can obtain this proposition. So the first condition corresponds to the effectiveness of the action of G and Hausdorffness of M as well as toric geometry. And the second condition follows from the maximalness of the action. And the third condition follows from the compactness and Hausdorffness of the quotient space of M over G. So okay. So anyway, so the triple coming from MG is controlled in this by this proposition. Okay. To state my result, let me introduce several notations. Let C1 denote the complex manifold with maximal torus actions. So this is what we want to consider. So let C2 denote the triples which satisfies the proposition as I showed before. And we have a map from C1 to C2. So namely, so we have assigned to MG as a triple. This is a fan, this is a vector space, and this is a Lie group G. Okay. And for a triple in C2, let x of delta denote a toric variety associated with delta, and let capital H denote the image of exponential map of her. So this is a subgroup of Geshi which acts on the toric variety. So I have also obtained the following theorem, but while preparing my paper, Lawrence Battisti showed the following. So the action of H on x of delta is free and holomorphic and proper. So the quotient space is a complex manifold. Moreover, the quotient space is compact, so we have a closed complex manifold. And now we consider torus action, compact torus action. So by definition, so G acts on the toric variety, and this action descends to the quotient space. So it's not difficult to see that the action on the quotient space is maximal. So this is an element in C1. So we have a map from C2 to C1. So feature signs. So which sends the triple to the quotient of toric variety. Okay. So C1 is can you see? No. So C1 is the set of complex manifolds with maximal torus actions, and C2 is the set of triples satisfying certain properties. So we have two maps. No. So now we have two maps between C1 and C2. So the main result, my result is as follows. So we have two maps between C1 and C2, and then the F1 and F2 are inverses to each other. So namely, we have a one-to-one correspondence between them. So it turns out that the geometry and topology of our manifold can be described in terms of combinatorial object. So the triples of Fan and vector space and the compact torus. And let's recall that there is a one-to-one correspondence between toric variety and rational Fan. And if we restrict our attention to complete non-singular toric varieties and Fans, so this correspondence coincides with the correspondence between C1 and C2 given by F1 and F2. Okay, so let me explain the sketch of proof briefly. So as I said, C1 is a complex manifold. C1 is a set of complex manifolds with maximal torus actions, and C2 is a triples, the set of triples. So it's not difficult to see that the composition F1 circle F2. So this is So this is a map from C2 to C2 is the identity because the toric variety corresponds to delta is a very concrete object. So the quotient space is also a concrete object. So it's not. So we can show that the composition is identity by the straightforward argument. So the main difficulty of my result is that the composition so this is a map from C1 to C1 is identity. So namely, so if we start from a mysterious manifold, can we say that so this is equivalently bihomorphic to a quotient of toric variety? Okay, so let me explain the sketch of proof. So by definition of maximal torus action, there exists a point such that the dimension of compact torus plus the dimension of isotropy subgroup is equal to the whole manifold. And we can obtain the following equality. The codimension of the orbit is exactly the 2 times dimension of isotropy subgroup. And as I said at the beginning of this talk, the tangent space can be decomposed into the subspaces, and using this equality, we have that the subspace tangent to the orbit is exactly the subspace fixed by the isotropy subgroup. So in particular, the orbit is a complex submanifold of. So we can see that the orbit is a complex submanifold of M. So by definition of the complexified action, this orbit is GC invariant. So we can express G dot X as a homogeneous space. So put GM is equal to the GC over H. H is a global stabilizer of GC. Then G dot X, this orbit is GM over the isotropy subgroup. And this is a little bit technical part. So for this orbit, we can find a nice tubular neighborhood by using sweeping technique. So I mean we can find a very nice tubular neighborhood which is equivalent bihomorphic to this joint bundle. And we define the set of collection of cones and vector subspace for this open subset. We can define and we can show that the proposition for these pairs. Since so by definition of GM, so we have a quotient map from GC to GM, and this quotient map induces a principal bundle, and this total space is an affine toric variety because GC is an algebraic torus and G sub XC is also an algebraic torus, and this one and this one has the same dimension. So we can say that it's not difficult to see that the total space is an affine toric variety. And now we can construct I forget to say. So this is, as I said, this is isomorphic, equivalently bifomorphic to one of the tubular neighborhood, and we can group them so that the total space is an affine toric variety. So now, we have a principal H bundle on an open subset of M, and the total space is a affine toric variety, is toric variety. And by this theorem, we can say the quotient space is compact. So this open subset is compact. So we can say this union is open and closed, but the M is connected. So this coincides with the whole manifold. So we can say that our mysterious manifold is equivalently bihomorphic to the quotient of toric variety. Okay. And let me show you a non-equivalent version of my result. So for two triples, we said that G's are isomorphic if they exist a group isomorphism G1 to G2 such that the differential of this homomorphism, so this is a map from G1 to G2, induces an isomorphism between funds. And second, the differential of this isomorphism is also induces a map from G1C to G2C, and this induces an isomorphism between the complex subspaces. So namely, everything coincides with everything coincides through the group homomorphism. Then so this is a non-equivalent version. So for given complex manifold with maximal torus actions, the following are equivalent. So one is first, so these are weakly equivalently bihomorphic. So weakly means up to an isomorphism between G1 and G2. Second, M1 and M2 are bihomorphic. So namely, we can forget the group action. So finally, by applying F1, we have a triple for each complex manifold with maximal torus action. The third statement says that the G's are isomorphic in this sense. So namely, we can classify the complex manifold which admits a maximal torus action using the triples. Okay. I stop here. Thank you.